Thank you very much. I'm delighted to be here in the amazing city of Tokyo and talk to you about our lasers at OEwaves. Uh, today we've heard a number of very interesting talks about quantum computing, about quantum communication, distributed quantum computing networks, and also sensors have been mentioned. But what's behind all of this, in some ways or another, are lasers that are the workhorse that in many cases, in the case of quantum computers, for example, that rely on ions and cold atoms, they interact with ions and cold atoms. And in case of networks and so forth, they are really the workhorse of taking information from one node to another. So what I would like to talk to you about is mention very quickly why this is important and what it is that we do. What's the noise of the laser? What impact does it have on the operation of all these systems? And how we deal with that, and what it is that we do in order to help quantum technology in general in this particular area where they depend on photons in one way or the other. So the laser noise is really one of the important parameters that determines, for example, the fidelity of the qubits and has an impact on virtually all of these applications that I mentioned to you. And ideally, in systems that use lasers, you want to be limited, especially if they involve atoms and ions, you want to be limited only by spontaneous emission noise or shot noise. But that really doesn't happen because limitations from the laser noise interfere with that. And in particular, it turns out that not only the laser itself, the fundamental noise of the laser or the intrinsic noise of the laser is an impediment in these systems' operation and how well they would operate. But importantly, even how we use lasers to stabilize their frequency impacts. In particular, in the past couple or 3 years, it's been demonstrated that in the case of neutral atom systems, quantum systems, where Rydberg systems are used, Rydberg atoms are used, this is a very important consideration, and that really limits the fidelity of the qubits. So this is an important thing, and that's something that we've been trying to address. OEwaves itself is a company that was spun out of Jet Propulsion Laboratory of NASA and Caltech many years ago, and we have recently focused specifically towards photonic systems that come to the aid of quantum computing. An example of that, for example, this is the system for ytterbium ion, and it shows the lasers that are involved. I want to draw your attention to the clock transition, which is 435 nanometer. Turns out that lasers are not available readily at that wavelength, and people often have to double that, start with 871 nanometer, and double the frequency to get there. And why do you need this? Because the clock transition is a very narrow transition, and you have to have a laser with low noise that very efficiently interacts with the transition and excites it. This is both for excitation and readout. Our lasers are based on semiconductor lasers, and they're very small, and they're shown there in comparison to, for example, an iPhone. And we have other systems that are much larger. And importantly, these are semiconductor lasers, and they have the following advantages. They're tiny, they're small, they're robust, and they also consume very little power. These are the things that impact the system, quantum systems, and makes it challenging to build systems that are really practical and can be used and become commercialized. In order to really commercialize a lot of these quantum systems, you have to overcome these kind of difficulties associated with the size, weight, and power of the lasers, as well as the stability, etc. And what I like to do is also point out to the fact that while there are semiconductor lasers in a number of wavelengths, but not every wavelength is available from one vendor. So it's very difficult for one company to provide all these different wavelengths for all the applications. So as you'll see, what we use is a system that allows us to get any semiconductor laser and turn it into something which is very ultra low noise. And this is done by using these cavities that are called whispering gallery mode resonators. These are tiny optical cavities the size of a millimeter or so, a couple of millimeters. And what happens is that light circulates on the perimeter of these very tiny cavities, and the loss is very small. When the loss is small, the quality factor is large, and as a result, the modes of the cavity are very narrow. And these narrow modes allow us to go ahead and use them as a way to actually reduce the noise of the laser. So the way it works out is that light goes through the cavity, and this is the cavity mode, and then we couple light with evanescent wave coupling is called. In this case, we use a tiny millimeter scale prism that allows the field from the prism to interact with the evanescent field of the cavity, and then light gets coupled into it. And after that, some of the light that is circulating in the cavity actually gets back scattered due to Rayleigh scattering into the laser, and through a process that's called self-injection locking, injection locks the emission of the laser to the mode of the cavity. This is something that we developed and patented many years ago, 8 years ago or so, at OEwaves, and it's extremely robust. And one value of it is that it doesn't have any electronics, so it's a completely all optical system. And once that interaction goes, then essentially the light that has been filtered by the cavity is fed back into the laser, and the mode of the laser collapses because of that, and the laser becomes very narrow line. Importantly, if we go ahead and use the type of cavities that are shown in here, by the way, these whispering gallery mode cavities come in different varieties. In this case, we have silicon microspheres and crystalline resonators, which is something we use at OEwaves, the crystalline resonators. But they're also made out of wedge resonators, microtoroid resonators, and recently all kinds of different material used on PICs, photonic integrated circuits. But significantly, the quality factor of the crystalline cavity is the largest of any cavity that has been demonstrated. We've demonstrated quality factor of 10 to the 11, which is very large when you compare it to other systems. And having that kind of a quality factor, again, it means that the modes have very narrow bandwidth, and that narrow bandwidth provides a very good filtering capability. So here we show a semiconductor laser, which is at 1550 nanometers, and it is locked to the cavity, self-injection locked to the cavity. And as you can see, the noise of it, which is shown on the right side panel, and what we're seeing on the y-axis, this single sideband spectral density of the phase noise versus the Fourier frequency. And when we get a distributed feedback DFB laser, semiconductor laser, and look at its emission and measure its noise, is that red line that you see. And when we couple it to the microcavity, the Spring-Garrett mode resonator, we see that the noise is suppressed by 60 dB, by a factor of 1,000,000. And one of the advantages of this scheme is that you can take any laser at any wavelength that coincides, that falls within the transparency window of the microresonator, and use that to reduce its noise. This is very helpful because, as I mentioned before, different companies make different wavelengths, lasers with different wavelengths. So we can get those and use it with our crystalline microresonators, which have transparency windows typically that range from UV wavelengths all the way to IR wavelengths. And so we can take any laser essentially that falls within that transparency window and suppress its noise. As an example, this is a laser that we developed. This was under a DARPA project for a ytterbium ion clock. And what it shows is that we managed to reduce the noise of this laser. The phase noise is shown on the left-hand side. The frequency noise is shown on the right-hand side. And the noise that we achieved allows this laser to be locked at the level of 10 to the 14 stability at 1 second. And that's very important because this is not only you need to have a low noise laser to interact with the atom, but importantly, when you want to stabilize it, the level of stability that you can get has to do with how low the noise is. And in this case, as you can see, about 10 megahertz. At 10 megahertz, we go, or actually at 1 megahertz, we go below 1 hertz. So these are sub-hertz level lasers that are semiconductor lasers and in very small packages. This one has an output of 120 milliwatt, which is quite adequate for use for this clock, which was, as I said, an iron-based clock on a small PIC, photonic integrated circuit. As I said, the blue lasers are not readily available. Sometimes you can get them at some wavelengths, like 435 nanometer. We could manage to get the semiconductor laser, and we coupled it to the resonator, and we got some performance out of it. We really couldn't measure the bandwidth of the laser very accurately because of the fact that it was in near UV, but it was on the order of just smaller than 100 hertz. One of the advantages of this type of lasers that we produce is that we can laminate a actuator, a PZT actuator on the resonator. And if we apply a voltage on that PZT, it exerts a pressure on the resonator, and that pressure changes the index of refraction, causing the mode to shift. And that way we can go ahead and modulate the laser, which is something you need to do if you're trying to lock the laser to an atomic transition or to a cavity. And that locking requires a very low relative amplitude modulation, which is a parameter that's used, and that has to do with the nonlinearities that exist in the modulator. In this case, because of this scheme that we use, the system is very linear, and it allows us to get 80 dB lower RAM than below the level of the laser. And that minus 80 dB is very important because in order to get it any other way in systems that they use this kind of a stabilization, they have to use a very complex circuitry and try to do it this way. This is very simple. We just put a voltage on a PZT, and it actuates like that. As I said, these systems, whether they're rubidium, calcium ion, strontium and strontium ion, ytterbium ion, and barium, all of these systems are being used in quantum applications. And because of that, you have to have all of these wavelengths available, and that's very difficult to do for other systems, but we can manage that. And we've shown that we've done this. And these are for different applications, whether they're computers or networks or different applications of quantum technology, and especially sensors as well. I didn't talk much about sensors. Here's an example of some of these wavelengths that we have generated. We have done everything, of course, from, as I said, 440 nanometers to 4.6 micron in that range. As long as there's a semiconductor laser available, we can build the laser at that wavelength. And this is an important thing that we really offer to our users, which is we really customize the system for them. Now, we have our architecture is such that we assemble things like Lego blocks together, and the architecture doesn't change. But at the same time, it's amenable to customization as far as the wavelength is concerned. And that's something that we do, and is very useful. Finally, I like to talk about how do you measure the phase noise and frequency noise of the laser. And there are various different systems to be used for measuring of that. We have also come up with a system for the measurement of the noise of the laser, which has the highest performance, the lowest noise floor. And we can customize this again to any wavelength, or they're actually coming wavelength channels, and different wavelength channels to be covering different needs. And so in this way, not only we can provide the lasers to our users, but also the ability to measure the performance of the laser. And that's important, again, in complex systems such as quantum computers, that the noise that exists impacts the performance, but sometimes you don't know where the noise comes from. And this way, it allows the person to determine whether the noise is from the laser or not. So that's all I have to talk about, and I want to thank you for your attention.